Thank you. Thank you for inviting me to this conference here. I'd also, before beginning, I'd like to acknowledge the contributions of my co-author, Chris St. Cyr of Nasser Goddard, who got me started on this topic. Next slide. Key points of this talk. So if you want to check your email, just listen now and then you can do that. Number one, and this is really easily understood, is that the societal costs of electricity blackouts are very, very high. Two, a number of the challenges to electric power reliability are exacerbated by space weather. Space weather not being the sole cause, but space weather makes these things more challenging. Three, the most critical challenge has to do with a form of electric power known as reactive power. Okay. And number four, investments in both space weather and power grid forecasting, vulnerability forecasting, have the potential to enhance the reliability of the system. Next slide. Okay, here's your basic structure of the electric power industry. Your production takes place over here in a generating station, and the consumers are here on the far right, and every megawatt of power that gets to consumers goes through a transformer. The electricity is generated at low voltages. It's stepped up into higher voltages to enhance the efficiency of transmission. And that's both good and bad. It's good in the sense that it reduces the losses in transmission, but it raises risks to the system because these transformers are vulnerable to space weather. Next slide, please. Okay, what is the economic value of electricity? Did anyone here lose electricity during the June outages, July outages? What was the value of electricity to you? Enormous. Okay. We lost electricity, but then I live in Montgomery County. We lose electricity all the time.
It's a 10-minute event.
I was out cycling one day and going through my neighborhood. It was a beautiful, calm day, and one of my neighbors had his generator on because the power wasn't flowing that day. But I digress. Okay, the economic contribution. Okay, we spend about $370 billion a year on electricity, but that severely understates the true value of electricity to society. Next slide. For those of you who've had a course in microeconomics, you'll recognize our demand curve here. This is our hypothetical demand for electricity. Here's the price, here's the quantity. And the amount we spend on electricity is this area A. That's the expenditures on electricity, price times quantity. But the total value that we receive from electricity is the entire area under the curve, and which means that the electricity is giving us a very large surplus. Okay. So in this case, the consumer surplus for electricity is area B. So the total value exceeds the amount we spend. Next slide, please. And so while the wholesale price of electricity might be only $40 a megawatt hour, economists who study this stuff conclude that the loss of a single megawatt of electricity has an economic cost in terms of grief, in terms of loss, threats to safety, etc., of between $5,000 and $10,000. Okay. That's what the literature says. It's not me. Okay. That the value of lost load is huge. Indicative of this high value, it's not unheard of for the price of electricity at the wholesale level, which is normally around 40, 50 bucks, to shoot up to 1,000. Next slide. Here's an interesting day in the New York power grid where they have two prices for electricity. They have a day-ahead price, where you have an equilibrium price for the next day, and then you have a price in real time. And so the blue here is the day-ahead price, and the black is the real-time price. And something went wrong on this day. Something seriously went wrong on this day. And the price shot up to about $900 a megawatt hour. Now, you might say, well, that was just 1 hour. My context, though, is something went wrong. The reliability of the system was challenged on that day. And that this price spike represents, in some ways, one of those canaries in the mine, saying that something's not right. Next slide, please. Some stylized facts about power grids. In general, electricity cannot be stored in large volumes. There's no big battery out there. And if you doubt me on this, there was a company, it was A123. Anyone know what happened to them? They went bankrupt. Outcomes are highly dependent on the performance of transformers. Electricity flows on the transmission system follow not the laws of supply and demand, but the laws of physics, which means that the electricity flows based on the path of least resistance. And so you can get large differences between what is supposed to flow versus what actually flows. Next slide, please. And so here's our contract fiction. Here's a hypothetical power plant. Here's some consumers. And the contract fiction is that these guys are buying power from those guys, and we sign a contract to make it happen. But the electrons don't know that. Here, the reality is that the electrons move wherever the heck they want to, depending upon constraints in the system. If there's a constraint in the system, instead of moving to the consumer, they might go this way and this way. They might even go that way. Next slide, please. And here's an example of what I'm talking about. This is from an interchange in the Midwest of the United States. The horizontal axis is the scheduled flows of electricity. Okay? What's supposed to show up. The vertical axis is what actually shows up. Does anyone here see a relationship? Regardless of the space weather involvement in this mess here, you heard a lot about the smart grid. This is one area where reliability can be enhanced by better modeling. I couldn't help myself. That's a plug for what I'm trying to do. I have a model to actually straighten this out. Okay, next slide. Here's another series of interchanges in Canada. Okay. And normally, here's the scheduled flows, here's the actual flows. Here, in this case, the function is actually pretty well behaved most of the time. But look over here, and look over there. Here you have some serious deviations between actual flows of electricity and schedules. And right now what I'm doing is I'm making a model, I'm formulating a model, estimating that model, and the preliminary results say that I can forecast these actual flows based on 3 variables. The scheduled, temperature, and guess what else?
Space weather.
Space weather. Yeah, thank you very much. Go ahead. Next slide, please. Stability conditions. And the power system is almost exclusively an alternating current system. There's a target level system frequency with a desired level of voltage and current oscillations each second. The desired level of system frequency in most of the world is 50 times a second. Here in the United States, we decided to be a little different. It's 60. Japan actually has a very curious system. Half of Japan is 50 hertz, and the other half is 60. Maintaining the desired level of system frequency requires that supply and demand not just meet on average, but all the time. This is a very stringent condition. Next slide. System frequency falls when demand exceeds supply. System frequency rises when demand is less than supply. In either case, the reliability of the system, the power system, is challenged. System operators offset these electricity imbalances by deploying what they call balancing power. This balancing power is almost continuously deployed up or down to keep the system stabilized. Next slide. Here's the deployments of balancing power in the United Kingdom, specifically England and Wales, in October of November of 2003. And what's striking here are the large deviations. So in this case, someone had to come up with 1,000 megawatts of power like that. And someone here, they had to throw away 1,000 or 1,500 megawatts of power. So they're constantly balancing the system up when they need more power, down when they have too much power, to keep the lights on. And it's my contention that space weather makes this job more challenging. Okay. Next slide. And here's the system frequency in the United Kingdom for last September. Here's our 50 hertz, okay? This is what they're supposed to have all the time. This was a particularly challenging day. Their operational limits are the red lines. And you can see here that they actually surpassed their upper operational limit, meaning that this was not a good day on the power grid. Okay. Next slide. There's more to keeping the lights on, though, than simply the system frequency. That other thing is the reactive power. Reactive power, well, there's two types of power. There's the real power, this is the power that keeps these lights on. But then there's also the reactive power, which maintains the voltages on the system for system stability. Okay. And without that reactive power, you have a system that can collapse. Sources of reactive power include generators and capacitors. Reactive power is consumed by the transformers. Next slide, please. Excessive reactive power has been implicated in almost every major blackout. Excessive reactive power consumption, or deficiencies, has been implicated in almost every single major blackout. According to the Federal Energy Regulatory Commission, voltage collapse due to inadequate reactive power has been a contributing factor in a number of blackouts. Next slide. And here's some blackouts. You had the West Coast of the United States, France, Tokyo, England, Sweden, and Denmark. The Hydro-Quebec blackout of March 1989. FERC says this was reactive power problem, and they're right. But it was also a space weather problem. The United States blackout, United States-Canada blackout on August 14, 2003. Does anyone remember that? Okay. That blackout there, they had a task force, and they concluded that reactive power issues were a contributing factor. Next slide, please. Blackout originated in Northeast Ohio, cascaded into an area where 50 million people lived. The lowest possible estimate of the cost of this blackout was $4 billion. In my opinion, the true cost was much higher than that. Next slide, please. Here's a picture from space. Gee, it looks like there's this area right here. Looks like no one lives there. That's New York and part of Ontario. Okay. Next slide, please. Okay, so how does this all happen? Here's my picture of someone's picture of a transformer. And the point is that the space weather gives rise to these geomagnetically induced currents. They enter the transformer and they overheat the transformer and affect its performance. Next slide. So GICs have potential consequences for the amount of electricity that the generators actually upload onto the system. Because remember, they generate the electricity passes through a transformer. If that transformer is not working well, less electricity gets on the grid. The GICs also affect the flows, okay? And the GICs also can affect, for these reasons, the GICs can also lead to price spikes. Next slide, please. Here's another graph. This is from New York again. And what they do in New York is they actually compute what they call a congestion cost metric. And the blue is the day-ahead congestion cost. The black is the real-time congestion cost. And the red guy, that's my proxy for the geomagnetically induced currents. And you can see in this part of the grid, you know, the congestion costs are relatively trivial. Except when? Well, it's kind of hard to see because the red and the black almost perfectly coincide right there, where the congestion cost got up to about a little bit less than $800 a megawatt hour, which is a lot of money. But my way of thinking, what this is telling us is that this is my canary in the mine story, that the reliability of the system was being challenged. Next slide. Okay, reactive power again. The GICs lead the transformers to consume more reactive power. Next slide. And so here you see a graph. This isn't mine. I borrowed it from a fellow named Malinsky. Here are the GICs, and here's the reactive power consumption. And what you can clearly see is that the higher the GIC levels, the more the reactive power is being consumed. Next slide, please. John Kapperman has spent a lot of time studying this, and in the Hydro-Quebec collapse of 1989, he indicated that the GICs increase reactive power by a factor of approximately 8 over the course of about 6 minutes. Okay. Minutes later, the high voltage lines needed to deliver the electricity from the far north to the south, those high voltage lines tripped. There was an imbalance in the electricity. Supply didn't equal demand anymore, and the system collapsed. Next slide. Reactive power issues are not isolated to Canada. The PJM, which is these are the guys who keep the lights on in this room, the reactive power issues are also a concern for them. Next slide. PJM moves a lot of power around. They move it around long distances. They closely monitor these flows to make sure that they don't exceed the reliability limits. And when they do exceed the reliability limits, they redispatch generation and reschedule the flows to keep things safe. And PJM considers the adherence to these transfer limits to be one of their major challenges. Okay, next slide. When they redispatch because of the transfer limits being needed to be revised because of reactive power issues. They deploy a series of operations known as reactive off-cost. An off-cost operation is when they dispatch generation based on system security as opposed to pure economics. They want to keep the lights on. And so when they have a reactive off-cost operation, what they're saying is reliability is threatened. We're going to dispatch generation not on who can produce the cheapest, but who can help us avoid this transmission challenge. Next slide. My co-author and I, we published a paper this past spring, and here are the results. I'll spare you the gory details. Here are the results saying that there's a non-trivial number of these reactive off-cost operations that one of the contributing factors is space weather. Taking into account temperature and a host of other things that can affect these reactive off-cost operations. So space weather is just one of the things, and here we were able to disentangle its effect. Next slide. Can anything be done? Well, improved space weather forecasts would really, really help a lot. And what we ideally need are space weather forecasts that can tell the system operators a day ahead, okay, an hour ahead, what the level of the geomagnetically induced currents will be for their region. I'm doing a study on England and France and looking at the power flows between England and France. And it turns out that the GICs in France have a different effect on the flows than the GIC proxy from the United Kingdom. Both of them have impacts, but the impacts are different. So to make my model operational, to make it useful in terms of forecasting, I need that GIC forecast at the regional level. Okay, modeling and forecasting the vulnerability of the power system would probably also help. That the vulnerability of the system is not constant. The vulnerability changes based on terrestrial supply and demand conditions. Next slide. And here's a chart. I know it's a little hard on the eyes. My apologies. But the bottom line of this chart is this, is that the vulnerability of the system, this is the probability of a reactive off-cost operation in the absence of space weather, that the probability changes over time. This we can model. I'm pretty sure. This we can model. Yeah, we can do that. This we can conceivably forecast. It's not insurmountable. And so my view is that in this case here, this is the 5th percentile of the vulnerability. Here you would need a really, really major storm to make things go south. But when you're really vulnerable, the 95th percentile, a relatively minor storm could do the trick. So I guess the takeaway here is that we all think about severe space weather. And that's appropriate. But what I'm suggesting is that depending upon system conditions, even a relatively minor storm could have an adverse impact. Next slide. Okay, so these impacts again, I'll overuse it again. These impacts that I've been talking about, these are the canaries in the mine. Those price spikes I talked about. These reactive off-cost operations, those are the canaries. Those are indicators saying that even though we didn't have any major blackouts during solar cycle 23, the system was being challenged. Going forward, the vulnerability of the system is likely to increase unless we do something. It's likely to increase because of our increased reliance on intermittent generation. that's going to be traveling long distance. Your vulnerability, your transmission vulnerability increases with the distance of transmission. Next slide. And the good news is we can forecast the terrestrial vulnerability. These was enhanced reliability. Better forecasts would, space weather forecasts would help. Forecasts of power grid vulnerability would also help. Thank you very much.